A pleasant morning to everyone. My name is Joanna Marie Iikibo from Group 4, and today I, along with my group mates Fiona Gabion, Lian Yvette Reyes, Ken Adrian Dreo, Riangeline Hasmin, and Arme Eve Indaya, will be discussing about the electronic structure of an atom. But before we jump right into the topic, let's first observe these two models of a helium atom. The first one is in Bohr's model of an atom, while the second one is in the quantum mechanics version. A helium atom acquires two electrons, right? In Bohr's model of an atom, these two electrons orbit around the nucleus, like how the planets orbit around the sun, while the quantum mechanics model illustrates a different version, in which these two electrons are in orbital, or are in a region of space where they can most likely be found. Now, which model do you think is incorrect? Well, it turns out Bohr's model only works well with atoms with few electrons, and not for all multi-electron atoms. And quantum mechanics is proven as the best option in predicting the electrons in orbitals. And to be able to do so, the 4 quantum numbers are used. This unique set of 4 quantum numbers are very important as it determines the location and energy of every electron in an atom. It also describes different atomic orbitals, illustrated in different shapes that look like the ones in the picture. And we will describe these later on. The first quantum number is the principal quantum number, and this can be any positive integer represented by n. So it can be 0, 1, 2, 3, 4, and so on. Now try to recall your lesson in 9th grade where you discussed the Bohr's model of an atom. This model shows different shells, right, which an electron can occupy. And if you can remember, these are also the energy levels of the electrons. The first shell, or the innermost shell, is the first energy level, which in quantum numbers is n equals to 1. The second shell is n equals to 2. The third shell is n equals to 3, the fourth n equals to 4, and so on. So basically, the principal quantum number, or n, describes the energy level of the electron inside the atom. Moving on, the next quantum number is known as the angular momentum quantum number, or the orbital quantum number. And to understand this, what again is an orbital? An orbital is a region of space where there is high probability of where an electron might be. And this actually has a relationship with the first quantum number, as principal quantum number n represents the energy levels, and each energy level acquires one or more sublevels. And each sublevel has an angular momentum quantum number represented by L. And L can be any positive integer from 0, 1, 2 to n minus 1. So basically, L is less than or equal to n minus 1. Now looking at this table, there are corresponding orbitals to each value of L, and each of these orbital varies in shapes, which is why the angular momentum quantum number is important, because it describes the shape of the sublevels. Now when your n value is 1, your L value could be 0, because again, L is less than or equal to n minus 1. So when your L value is 0, the electron could be in the s orbital. When your n value is 2, your L value could be 0 or 1, and the electron could be in the s or the p orbital. And when your n value is 3, your L value could be 0, 1, or 2, and the electron could be found in the s, the p, or the d orbital. And when your n value is 4, your L value could be 0, 1, 2, or 3, and the electron could be found in the s, the p, the d, or the f orbital. Again, it's very important to be familiar with the L values and its corresponding shapes, so let's run over it one more time. When your L value is 0, you get these spherical shaped orbitals, which is the s orbital. When your L value is 1, you get these p orbitals, or the dumbbell shaped orbitals. When your L value is 2, you get the d orbitals, or these 5 complex looking orbitals. And lastly, when your L value is 3, you get these 7 more complicated looking orbitals. And just to make sure that everybody absorbed what I just said, let us have some few examples. If we have an electron found in the 4f sublevel, what is its n and l value? Well, its n value is 4, while its l value is 3. Why? Because the number in the front always represents the energy level of the electron, while the letter beside it describes or serves as a clue of what shape the orbital might acquire. And if you remember what I shared earlier, if your L value is 3, then your electron could most probably be found in the f orbital.
Magnetic quantum number. Magnetic quantum number is denoted by the symbol m sub L. It is a number described as the orbital within a sublevel. An orbital is a mathematical function describing the location and wave-like behavior of an electron in an atom. An orbital can have a maximum of 2 electrons, which can have either an upspin or a downspin. So, to further understand what exactly is a magnetic quantum number, first, we must know the connection of an angular momentum quantum number or L and a magnetic quantum number m sub L. So, if L is 0, its m sub L is 0. If L is 1, its m sub L is negative 1, 0, and 1. If L is 2, its m sub L is negative 2, negative 1, 0, 1, and 2. If L is 3, its m sub L is negative 3, negative 2, negative 1, 0, 1, 2, and 3. So, m sub L are numbers between positive L and negative L. So here is another example. If L is 4, then m sub L are numbers between negative 4 and positive 4, which are negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, and 4. So here are another examples. 2p sublevel has an n of 2 and an L of 1. So its m sub L can either be negative 1, 0, and positive 1. Another one is 3d sublevel, which has an n of 3 and an L of 2, which means its m sub L can either be negative 2, negative 1, 0, 1, and 2. Spin quantum numbers or electron spin numbers are denoted as m sub s, and it describes the angular momentum of an electron. A spin quantum number can have a value of positive or negative 1/2 depending on the last electron. If the electron is an upspin, its value is positive 1/2, and if it's a downspin, its value is negative 1/2. So to further understand this, here is an example. An example is 3d8th electron, which has an n of 3 and an L of 2, which results to having 5 values of m sub L, which are negative 2, negative 1, 0, 1, and 2. So, to draw the 8th electron, I first draw 5 downward or downspin electrons, then added 3 upspin electrons. So, the last electron is an upspin, which resulted to being m sub s being positive 1/2 and m sub L being 0 because the electron ended in the value of 0 or within 0. So here is the example. But what if we begin with an upspin? So here is a variant or another illustration of the example. So I first draw 5 upspin electrons, then added 3 downward or downspin electrons, which resulted to downspin being the last electron, which means having its value as negative 1/2, but the value of m sub L still remains 0, and n and L does not change, which proves that m sub s can either be positive or negative 1/2, and n, L, and m sub L will not change even though m sub s is a positive one half or a negative one half.
The filling of electrons into the orbitals of different atoms takes place according to the Aufbau principle, which is based on the Pauli's exclusion principle, the Hund's rule of maximum multiplicity, and the relative energies of the orbitals. But first, let's discuss the first principle, which is the Aufbau principle. So what is the Aufbau principle? The Aufbau principle, from the German word Aufbau, meaning building up, describes a model building method in which an atom is built up by progressively adding electrons. As electrons are added, they assume the most stable shells with respect to the nucleus and the electrons already present. The Aufbau principle states, in the ground state of an atom, electrons are filled into atomic orbitals in the increasing order of orbital energy level. In other words, electrons fill or occupies the lowest energy orbital first in the ground state of an atom before filling the higher energy orbitals in order to minimize the total energy. Now, the Aufbau principle is utilized to understand the location of electrons in an atom and their corresponding energy levels. The order in which atomic orbitals are filled is given by the N plus L rule, also known as the Madelung rule, an empirical rule for determining the order in which atomic orbitals are filled. In this context, N represents the principal quantum number, and L represents the azimuthal quantum number. With the sum of the principal and azimuthal quantum numbers, we can determine the orbital energy level. Mathematically, the dependence of energies of the orbitals on N and L are quite complicated, but two simple rules are stated. According to the N plus L rule, lower N plus L values correspond to lower orbital energies. Thus, orbitals with the lowest values of N and L will be filled first. The other rule is, if two orbitals have the same value of N plus L, the orbital with lower value of N will have the lower energy. The order in which the energies of the orbitals increase, and hence the order in which the orbitals are filled, is as follows. From the illustration, starting from the top, the direction of the arrow indicates the order in which orbitals are filled, that is starting from the right top to bottom left. And each diagonal arrow corresponds to a different value of N plus L. According to N plus L rule, the values L is equal to 0, 1, 2, 3 correspond to the S, P, D, and F orbitals respectively. An Aufbau diagram uses arrows to represent electrons. When there are two electrons in an orbital, the electrons are called an electron pair. Electron pairs are shown with arrows pointing in opposite directions. According to the Pauli exclusion principle, two electrons in an orbital will not spin the same way. That is, an Aufbau diagram uses arrow pointing in opposite direction. An arrow pointing up denotes an electron spinning one way, and an arrow pointing downwards denotes an electron spinning the other way. But if the orbital only has one electron, this electron is called an unpaired electron.
The Pauli exclusion principle. The Pauli exclusion principle is used to determine the electron shell structure of atoms. It helps to predict which atoms will share electrons and participate in chemical bonds. The Pauli exclusion principle states that no two electrons in an atom can have the same set of four quantum numbers. This was proposed by Austrian physicist Wolfgang Pauli in 1925 to account for the observed patterns of light emission from atoms, and in 1940 he extended the principle to all fermions in the spin statistics theorem. The exclusion principle subsequently has been generalized to include a whole class of particles of which the electron is only one member. The subatomic particles fall into two classes, based on their statistical behavior. Those particles to which the Pauli exclusion principle applies are called fermions, and those that do not obey this principle are called bosons. Particles obeying this principle have a characteristic value of spin, or intrinsic angular momentum. Their spin is always some odd whole number multiple 1/2.
In the modern view of atoms, the space surrounding the dense nucleus may be thought of as consisting of orbitals, each of which comprises of only two distinct states. The Pauli exclusion principle indicates that if one of these states is occupied by an electron of spin 1/2, the other may be occupied only by an electron of an opposite spin, or spin negative 1/2. An orbital occupied by a pair of electrons of opposite spin is filled, and no more electrons may enter it until one of the pair vacates the orbital.
Hund's rule. So the Hund's rule states that first, every orbital in a sublevel is singly occupied before any orbital is doubly occupied. So to further elaborate this, or to further explain, before pairing up, electrons always enter an empty orbital because electrons are negatively charged. Therefore, they repel one another. Electrons prefer to occupy their own orbitals rather than share an orbital with another electron to reduce repulsion. Furthermore, quantum mechanical calculations have shown that the electrons in singly occupied orbitals are less effectively screened or shielded from the nucleus. Second, all of the electrons in singly occupied orbitals have the same spin to maximize the total spin. To elaborate this, or to explain, unpaired electrons in singly occupied orbitals have the same spins according to the second rule. Technically speaking, the first electron in a sublevel could be either spin up or spin down. Once the spin of the first electron in a sublevel is chosen, however, the spin of all of the other electrons in that sublevel depend on the first spin. To avoid misunderstanding, physicists label the initial electron in an orbital as well as any other unpaired electron as spin-up. So next, when an electron is assigned to an orbital, it first tries to fill all of the orbitals with the same energy. This is also known as degenerate orbitals, before coupling with another electron in a half-filled orbital. Atoms in their ground states have the most unpaired electrons conceivable. So, for example, consider how electrons behave in the same way that the same poles on a magnet would if they came into contact. So, as negatively charged electrons fill orbitals, they first strive to go as far away from each other as possible before having to pair up. So, in summary, all unpaired electrons in an atom's ground state structure have the same spin orientation. As a result, electrons tend to occupy all three orbitals and not couple up, resulting in the atom's spins adding up to produce a general vector.
So, before I give you an example of the orbital diagram to represent the electronic configuration of atoms, let us first define what is an orbital diagram. So, an orbital diagram is used to determine the paired and unpaired electrons and the distribution and direction or spin of the electrons. So take a look at this. These are the subshells, the S, P, D, and F. S can hold 2 electrons, P can hold 6 electrons, D can hold 10 electrons, and F can hold 14 electrons. However, each subshells have a different number of orbitals. S subshell has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7 orbitals. So take note that 1 orbital can hold 2 electrons only. Now let us proceed to the first principle, which is the Aufbau principle. In this principle, it is stated that lower energy level must be filled first before filling the next energy level. So let us use lithium for our first example. Lithium has an atomic number of 3, therefore the number of electrons is also equal to 3. The electronic configuration of lithium is 1s superscript 2 and 2s superscript 1. So how will we graph this? Let us first draw the orbital diagram. So remember that the s subshell has only 1 orbital. So yung pagfill is from lowest energy level to highest energy level. So sa 1s, we will be needing 2 electrons, in which the first electron should be placed in an upward direction and the second in the downward direction. Sa 2s naman, we will only be needing 1 electron, it should be placed in an upward direction. And yes, this is an unpaired electron. The Pauli exclusion principle states that no two electrons can have same 4 quantum number. Electrons in same orbital must have opposite spins. For the example, let us use the element beryllium with an atomic number of 4, and the number of electrons is also equal to 4. So the electronic configuration of lithium is 1s superscript 2 and 2s superscript 2. So let us draw the orbital diagram. So 1s, we will be needing 2 electrons, in which the first electron should be placed in an upward direction and the second in a downward direction. So kasi nga sabi, electrons in same orbital must have opposite spins. So sa 2s, we will be needing 2 electrons then kasi bali 4 electrons yung kailangan sa beryllium. The first electron should be placed in an upward direction and the second in the downward direction. Hand rule, electrons are filled in one at a time before pairing. Let us consider the oxygen atom. So 1s can accommodate 2 electrons, in which the first electron should be placed in an upward direction and the second in a downward direction. So sa 2s, it can also accommodate 2 electrons, in which the first electron should be placed in an upward direction and the second in a downward direction. For 2p, we will be following Hund's rule, where in the orbitals of the same subshell, electrons are filled singly first before pairing starts. Therefore, 1 electron that is in an upward direction will be placed on the 3 orbitals to be followed by 1 electron that is in a downward direction pairing the first orbital.
And this concludes our discussion about the electronic structure of an atom. Thank you everyone for listening and have a nice day.